Hey everybody, I'd love to introduce Siddhartha Mishra from ETH Zurich. We've been focusing on a lot of physics-guided machine learning that's really constrained by the physics of the problems. Welcome, Siddhartha.
Thank you very much, Greg, for this opportunity to talk here, and apologies for the slight delay in starting due to joining issues. Okay, so I'm going to talk about AI for data-driven simulations in physics, and this is a very interesting topic with a lot of interest from academia and industry in the last 3-4 years. So let's see what's going on here. So first of all, so the bedrock, if you remember my title, it's about simulations, it's about data, and it's about AI. But the core of it is applying these concepts in physics. So the starting point, of course, in physics is that you have mathematical models, otherwise you can't simulate physics. And the core of these mathematical models are often partial differential equations, objects that you might have seen in your freshman physics and math classes. So partial differential equations, or PDEs for short, these are the language of nature, and natural phenomena, physical phenomena at all scales are modeled by these, for instance, all the way down to electrons with the Schrodinger's equation, to the largest scales in terms of Einstein's equations, and everything in between, fluids with the Navier-Stokes equation, solids with elasticity equations, biological systems with reaction diffusion equations, and so on. So there's a very rich panoply of phenomena that are modeled by partial differential equations, and we can write them in many, many cases. But as we know very well from high school and first-year university, that just because you can write down an equation doesn't mean that you can solve it, at least by hand. So what can one do? Means, as I said, it's not possible to find some analytical solution formulas for PDEs. So if you want to make predictions, if you want to understand what's going on, then you have to resort to something different. And the different is what are called numerical methods. Many of you might have heard of them. They are under different names: finite difference, finite volume, spectral methods, and so on. And the idea is that you take this system of PDEs, and solving them is reduced to doing some computation on a digital computer. And this is the essence of these numerical methods. And this has been a tried and tested methodology for the last almost 100 years, certainly since the Second World War, so at least 80 years of pedigree there. And this is extremely successful. Even in my own lab, we are able to simulate very complex physical systems, core collapse of supernovas, the dynamics of clouds, flow past a rocket, tsunami generated by a rock slide, some manufacturing problems, waves in the solar atmosphere, and so on. Very different kinds of physics, and they're all simulated using the same sort of techniques. So very successful. However, there is a catch, and this catch is, so there are several points of caveat here. And the first thing is that these numerical methods, even though computers have become more and more powerful, the kind of problems we want to solve have become harder and harder computationally, and this ends up having a humongous computational cost. Just to give you some sense here, so this is a simulation, fluid dynamics. I have some initial conditions. I solve the Navier-Stokes equations. I solve it on a supercomputer that we have access to here in Switzerland. And the point is, for a single simulation with lots of degrees of freedom or computational elements in it, a billion per time step, as you can see from here, this is, it takes about 100 hours on a GPU. It's a very high resolution simulation, as you can see here. So it takes about 100 hours. But the point is that it's a very complex physical system. The seminar is about complex physical systems. This is as complex as it gets, because if I make very tiny, tiny little perturbations of the initial condition, not perceptible to our eye, you can still see that the solution changes dramatically in time. So the problem is not a single one-line prediction problem. It's rather what is called an uncertainty quantification problem. We want to understand the statistics of the system at hand. And that requires sampling from a probability space, which is, you'll see it later, thousands of simulations. And then this all adds up, because these can be done in parallel, but each of these is 90 or 100 GPU hours, sorry. So the whole thing is 100,000 GPU hours. So that's $100,000. And this is where the computational cost is. And later on, you'll see even more stark numbers as we develop the lecture. So you need to solve these PDs much faster, at least at large scale, than before. But that's not the only issue. I think the big issue is what is shown here, which is that physics is often unknown and imprecise. Let me give you a very concrete example. So this is the Earth system, which we use in our weather and climate models. So what we do here is that some parts of the physics are very well known. You can think of the flows in the atmosphere and the ocean. So this is Navier-Stokes equations. You can think of radiation. This is a radiative transfer equation. Very classical physics, in some sense, very well understood. But there are other physical effects, phenomena, the role of vegetation, forest cover, the role of land, aerosols, tiny particles in the atmosphere. Now, the details of the physics here are very intricate, and it's almost impossible to resolve them. So you simply you can't write down the PDEs or the governing equations from scratch here. So there's a challenge, and this is often when we deal with real systems, particularly in biology or material science, this comes in quite a lot, and it ends up with what are called sim to real gaps. Now, in robotics, this is a very, very well-known concept. It's the same here in general in physics, that even if you have the best simulator, you end up making modeling errors, and these are non-improvable by increasing your compute, right? So this holds true, and so we have to think beyond this sort of traditional paradigm where we can write down equations and try to solve them on computers. So what do? What we have is, of course, data. Sometimes a lot of data, sometimes not enough, but we have some data, we have some knowledge of physics. Can we sort of combine them to learn the solutions of PDEs? So this is going to be sort of the main element, the main sort of theme, spine of my talk, the narrative spine of my talk. So now we have to be a little bit more precise mathematically. What does it mean to solve a PDE from data, right? So it depends on a perspective that is very common these days, that whenever you have PDE, you can think of it as a system. So I don't know how many of you are familiar with this particular PDE, but it's a very prototypical first-year PDE that you write down. For instance, it models how the voltage is diffused out if you apply some forcing or some current or something like that. Or if you apply pressure, how does this pressure get distributed inside a rock? Nevertheless, the point is that you have some input. This is a field, conductivity or permeability field, and you have some output. This could be a pressure, it could be a temperature, a concentration, or something like that. So the PDE itself, or the physical system that is modeled by the PDE, takes some inputs and it churns out some outputs. And the point is that these inputs and outputs, these are infinite dimensional. These are fields. So they have a value in every point in space. And if you have a temporal problem, also every point in time. So this input to output mapping, this field to field mapping is infinite dimensional. Hence, it's a operator. And this is what is called the solution operator of a PDE. And this is what we want to learn, because when we change the input, we just apply this learned operator and we extract the desired output. So this is a basic sort of learning task in that sense. But and we want to learn these objects from data. So that's the essence here. But once we want to learn something from data, we have to put some restrictions, some distributions on the data, some modeling assumptions on the data. So for this talk, I'm going to assume that there is a probability distribution on these fields, infinite dimensional functions, and this probability distribution, and you can sample from this probability distribution, and I could have added some noise to the output, but I didn't do so for convenience. This can be done in principle. Nothing holds us back. The learning problem is that given these input-output pairs, given the drawn from the data distribution, finite number of them, n is a number here, I have to learn what is called a push forward, which describes the action of the solution operator on this particular distribution. So that is in distribution learning in some sense. So this is the key object that we want to learn, mathematically very, very well defined. And we have to learn this object using neural networks. Right? This is the age of AI. Neural networks permeate every aspect of our lives. So how are we going to do that, right? So the point is, now there is a caveat here, because neural networks, whether you have the standard MLPs or CNNs or transformers, whatever you're thinking of, these are mappings which take finite dimensional inputs, potentially very high dimensional, and produce very high dimensional outputs. Think of video generators, right? This is like 1 million or 2 million output points in a vector. But nevertheless, these are finite dimensional. But as I told you in the last slide, the learning task that we have, also called as operator learning, is essentially an infinite dimensional task. The inputs and outputs are functions. So you ended up with trying to reduce the infinite dimensional in principle problem into a finite dimensional computational problem. And this is the core of numerical analysis, which is what I have studied ever since my PhD. So how do you do that? Now, there are different ways to do it. Perhaps conceptually, the simplest is the following. That if you think of neural networks are mapping between finite dimensional and finite dimensional spaces. So what you do is that you take an input vector, you multiply it with a weight matrix, add a bias vector, and apply nonlinearity component-wise, and you stack these things together as compositions. That's neural networks. They work very well in 5 dimensions. So Nick Kovacsky and his co-authors from Caltech some years ago, they said, formally or conceptually, why don't we extend it, sort of mutatis mutandis, to infinite dimensions? So we keep the compositional structure. Now, for every hidden layer, what we do is instead of having a vector input, we have a function input. So the output will also be a function, which can be evaluated at any point in space or time for that matter. And then instead of, so this is the input. So this bias vector can be replaced by a bias function, learnable or parameterizable. And the key object is here. So this matrix vector multiply gets replaced by its canonical infinite dimensional extension. This is what is called a kernel integral operator, right? So you multiply against a kernel and then you integrate. So this is the basic idea here. And then you apply the nonlinearity pointwise, which was the original proposal. And some years afterwards, we said, no, this can also be made into something non-local to reflect the infinite dimensional nature of this problem. But nevertheless, this is something that you can write down on paper. Computation has to be done in finite dimensions, so you have to discretize these continuous objects. And different choices of discretization essentially leads to thousands or tens of thousands of examples of neural operators these days. So these are the infinite dimensional extensions of neural networks. Let me provide you with a couple of examples.
Question.
Yes.
So please. Yeah, how should we think? I mean, this is a challenging concept. So how should we think about the functions being learned? Should the mental model be like a time step function where is that what we're learning here? And it's like a function for the field before, function for the field afterwards, or is there a different mental model?
Time stepping is one potential mental model, but I would think of it as you could we can write down this expression, right? There is no question about that. Mm-hmm. The choice is you should think more of discretization in space at the moment. So just imagine that you are on a Cartesian grid. I have some concrete examples in the next slide, so it will be much clearer, the mental model. So what you do is that you break down the function into a set of finite dimensional pieces, for instance, or represent them in terms of a basis. So that's how you should think of at the moment as a mental model. Time stepping could be one potential way, but I'll come to that in a bit. Okay.
Okay.
So if you see the example in the next slide, things will be clearer. Okay. Just have that. Bear with me on that. So let's take some examples just to see how this is conceptualized, right? So one example, or one very large class of examples, is provided when this kernel is essentially a translation invariant kernel, because a lot of physics is translation invariant. So it makes a lot of sense to have a sort of a translation invariant ansatz here. And now once you have a translation invariant kernel, at least you can write this down as a convolution. And there are different ways in which you can instantiate these convolutions. So the original proposal by the same set of authors as the one before was to do it in Fourier space. So this is how it works. You start with a function. You take a Fourier transform. You can always take a Fourier transform of a function. You can compute it very efficiently. Then use a learnable Fourier multiplier here. Take an inverse Fourier transform. And then some residual connection for stability, but essentially apply the nonlinearity physically in space at every point. And this is one way to do it. You'll see in the next slide what are the issues with that. Another way to do it is the sort of traditional ML way, which is to have the convolutions, but you can't just apply the convolutions sort of without making any changes. So what we proposed here is to keep convolutions with sort of narrow banded kernels. But then we decided to modify the activation function, because after all, there's an activation function, and we made it non-local in a very precise way, which is to fight what are called aliasing errors. Because when you apply nonlinearities to functions, you end up with aliasing. People in signal processing know this very well. So you'll see in the next slide what are the effects of that. So this was one particular or two particular choices that you could come up with. And the mental model that someone asked is precisely instantiated here. So just imagine that you have an operator. So there's a Navier-Stokes equation, 2D for simplicity. So what happens here is that you have these two vortex layers and there is a shear. So because of the shear, you have these vortices which are generated. And what you want to learn is, given a final time and given the initial conditions, how is my solution going to look like? So this is the basic idea. But we do it in velocity space, and then we can compute the vorticity. So now you can apply, for instance, a CNN, means it's the simplest thing, it's an image, so you can apply a CNN. And what happens when you apply a CNN unit, for instance, is that for a fixed resolution, so you divide this input function and the output function into a grid, right? 64 squared grid. So that's the mental model. And then you learn something. So the training and the testing is done at the same resolution, and then you get some error. But the problem is that this is a function, right? So I can discretize it into 64 squared pixels or to 128 squared or 32 squared. This is at my choice. It's not an image, it's a function. And then when you change the resolution, the method totally does not generalize. So this is the reason why you cannot directly apply a unit here. Means you have this loss of generalization that happens. Instead, with FNO, with the Fourier neural operator, this is meant to sort of create that, to destroy that effect. You see that it when you increase the resolution, then it functions quite well. But when you reduce the resolution, it still doesn't. This is because of the so-called aliasing errors. You can see them here. So what we did in our construction is that we modified units or modified CNNs to take into account the fact that these are actually functions which can be discretized at any level of resolution, and the details are not important here. Then we get a flat line, and we even have a theorem to say that indeed this will be resolution invariant. So this is the main advantage of taking this construction that I said. But in general, if you are happy with just learning at one resolution, you can do that with a unit. But this is not what you want to. You want to learn across multiple resolutions, and you want to generalize very well. So that's the mental model that you should think of. Now, these are difficult concepts, but think of the kernel. This is sort of the essential construction here. So why should we use just a linear kernel? After all, convolution is a linear kernel. Although nonlinearity is sitting in activation, why can't we use a nonlinear data-dependent kernel, right? This is completely fine. We can do that. And the simplest, or not simplest perhaps, but the most useful example is to rewrite attention as essentially a realization of a nonlinear kernel. And this is precisely attention, very easily written down in infinite dimensions, means you don't lose anything. And then you have this kind of a construction here. And of course, in order to have the computational cost reasonable, you have to use vision transformers or swing transformers, depending on the applications that you have. So essentially, once you write things in terms of kernels, and once you have the correct discretizations, particularly at the level of nonlinearities, you can use a lot of standard ML techniques to do this. You have convolutions, you have attention, you have state space models, a lot of things open up, right? So this is the main point. Now again, this is in some sense a solved problem in 2D on Cartesian domains, like the problems that I showed you here. There are many architectures which work equally well, some works better than the other, and so on. But reality, particularly in engineering, is not about Cartesian domains, and it's certainly not about 2D. Reality is really 3D. So in particular, when we are talking about arbitrary domains, so remember that what I have discussed so far is here, Cartesian domains, image-like architectures do well with some minor twists, right? But in reality, what you have is you have airfoils or aircraft, then the point cloud that describes data on the aircraft is not Cartesian at all, or you have a race car with a very complex grid around it and so on. So to have any kind of engineering realism, your methods have to generalize from the Cartesian domain. And there are, again, various different ways of doing it. One way that I'm going to present is quite effective these days. And this is to combine somehow graphs and transformers, because you can do end-to-end graphs, or you can potentially do end-to-end transformers. But in terms of efficiency, this construction is quite suitable. So this is again from my lab. And the idea is that you want to essentially do processing. I don't know how well you see the screen, but you do processing on a very complex grid, which is data on these blue points. This is the data around the airfoil. And what you want to do is to transform this data into some tokens or features on a Cartesian grid, because on a Cartesian grid, we know how to process data, right? And to do this processing, this transferring, this mapping, what we do is we use essentially some graph neural networks, some lightweight graph neural networks. These are not based on message passing, but on information aggregation locally in a hierarchical manner. And then we have what are called geometry-aware tokens. So they have information about the geometry because it had a very complex geometry. Now you're on a Cartesian grid. So where is the information about geometry? Instead of being in physical space, it is now in this feature space. So once you are in feature space, you can just use a transformer, a vision transformer, for instance, and then you can map back. So this is the basic idea. There are many, many technical details here, but this is not the time or place to talk about them. So the advantage of doing this is now you have extreme flexibility in terms of geometry. So we can, for instance, do a hypersonic or supersonic, in this case, flow past an airfoil or past a cylinder. The features are slightly different. The shock waves are very different. You can do elasticity, plasticity actually on the domain, and many, many other problems. And this is accurate.
So a question
as
about
I said.
this.
Yes, absolutely. Please go ahead.
If I may summarize just kind of the core idea and tell me if I got this wrong. The core intuition is that you have some kind of functional basis and you represent every function in terms of that basis, possibly a learned basis. And then the discretization that used to be in the input space now becomes, it sounds like, in the number of basis elements you use. So like number of frequencies if it was a Fourier domain.
Yes.
Is that a good summary?
It's a good summary. It's a very good mental model. It's not entirely accurate though, because we never, if you put that sort of a basis structure, this can be done. In fact, the very first constructions in this field were based on these ideas. Then the point is that the expressivity of your model is restricted in some sense by this essential linear representation, right?
Yep, of course.
So now, but it's a good mental model. In fact, when you prove theorems, you try to essentially do that, right? But the advantage of keeping this construction nonlinear with the learned, not just a learned basis, but saying that going through the basis route is one possible route, but we allow the model to explore other routes during learning, this gives us a lot more freedom. So in practice, we do a lot of analysis on this. You don't really realize it in practice. You allow your architecture to be general enough to have this learned basis interpretation, but it chooses something else. So this is sort of, particularly when you have attention, you have very complex interactions that take place. So it's a good first order model, but I think the second order effects are very important here.
That makes sense. And then the second thing is here.
Yes.
It seems like you've replaced traditional, regular function on Cartesian grids, which are easy to define, with effectively GNNs, which say that I am a function of my graph neighborhood, and that's it. Is that right?
This is essentially the case. So it's a very local method in some sense. We have some global features attached to it. And then we map that information just to a sort of a feature space, right? So all that the GNN does is that it doesn't do the heavy lifting. It produces some reasonable features. We call it geometry-aware tokens in the sort of physical space, a Cartesian space, and then the transformer is supposed to learn the complex identities here, the complex features here, right? So essentially, you should think of this as an encoder. In fact, it's even called an encoder. All that the GNN does is that it encodes complex geometric information into a nicely behaved feature space. And then it is decoded. So actually, as an autoencoder, if I did not have this block, it has some good properties. It's not a variation autoencoder, it's a plain vanilla autoencoder, but it essentially does just a transformation. It's not supposed to do very complex things, if it makes sense. So the heavy lifting, because you need global dependencies. If you just use GNNs, you need deep GNNs, and then, efficiency-wise, you suffer. So you need to still use attention somewhere, and that is done in latent space. So the latent space in that sense is very rich.
Got it. And in a lot of ways, this seems like a generic neural network, actually, because you're using a lot of the machinery from everywhere else. And
yes.
If I may, it looks like the major difference is that this is discretization invariant, and they're fine sticking to a consistent discretization. Whereas for you, because your function spaces, you very much want to escape it.
Yes, of course. That is a correct interpretation. One has to be careful because you have to prepare your inputs and outputs in order to make it discretization invariant and so on. But let's say modulo those technical details, this is correct.
Excellent. Thank you very much.
Yes. So as I said, you could do graphs. You could use a GNN end-to-end. So this is also a GNN from my lab, which is as effective. The problem with GNNs end-to-end is that they are not very scalable. Means it's sort of, because you'll see later on that we will deal with 20, 30, 40, 50 million input points, and then the GNN is too, it's not scaling. At least we don't know how to scale it, right? So it's sort of, you can see that as the input increases to 100 million points, the GNN's throughput, training throughput really drops, whereas the architecture with GNN plus transformers, all the heavy lifting is done by the processor, the transformer processor, and then it remains more or less invariant. So that's the basic idea. It's a scalability argument more than anything else. And once you have this scalability, then you can attack 3D problems, because this becomes, you need that. So here's a data set from MIT. The idea is that you have the input shape of a car, passenger car, not race car. We have done this on race cars, but this is more confidential information. Then what you have is that you give some flow conditions, and the task is to return things like the pressure on the surface and the wall shear stress and so on. So this architecture does quite well. It's pretty accurate. You'll see in the next slide. But the main advantage of it is that earlier, this simulation on the traditional numerical method, this is like 400 CPU hours. These are not GPU compatible codes yet. 400 CPU hours, it would have been 40 on the GPU, not less. But now this takes 1/3 of a second. Right? Inference is very, very, very fast. This is the advantage of neural networks. As I said, it's very accurate, and it's half as accurate or double as accurate, half as error prone as previous architectures. And it's simply because we are able to process all the 500,000 nodes at one go. So scalability is what gives us accuracy, not necessarily the model size. You can really do even more complex benchmarks. So this is a data set from NVIDIA. So now the number of the same problem, but the physics becomes different. You have something called LES, much more precise physics. And this is 9 million surface nodes. So you have really a lot of surface nodes. The accuracy is quite decent. But again, here it was a very, very big computation, 60,000 node hours. And we can do this inference at least in 14 seconds. So there's a real gain in that. And you can do this at the level of a full aircraft. These days, there are some even more complex data sets coming out of NVIDIA. And again, the same story. Well, once you're able to train with this realistic grids, then inference becomes very, very fast. Okay, so this seems to be a very, very good story, right? Now let me put some, yes, please, go ahead.
What makes it fast? Is there there is this common thing of neural approximations are faster than numeric things, but ultimately you are effectively solving the same equations. So what regularities are you really leveraging to allow you to speed up?
This is a very, very good question. So let me try to answer it with this, right? So now, how does numerical simulation work? So you give me the shape of the car. The first thing I have to do is I have to generate a grid around it, right? Now, by the way, the grid is not included in the 61,000 node hours, but the grid is, I have to generate a grid around it. This takes forever. This is a very complex process. Each time the shape of the car changes, the grid also changes. There are some techniques to do it in a continuous manner, but these are not the easiest, right? So you need to generate a grid. Then what you have to do is that this is a flow, but you're interested in a steady state behavior or some time average behavior. So you have to use some time stepping technique. And so you have to step forward in time. So you have to take some small time steps, and you have to take, because the physics or the numerics is very, very constraining. But you're not interested in this very, very small scale dynamic behavior, because this is of no interest whatsoever. These are the tiniest eddies in the system. So now you have lots and lots and lots of these time steps, and you have very, very tiny resolutions, because to stabilize the flow, to capture the smallest features, you need all this information, right? So there's a lot of information, a lot of flops that go in, and that's why the traditional numerical method is very, very sort of, let's say, expensive. But now for a neural network, you're not training on that kind. You don't need to train on that kind of data. You can downsample the data to much coarser grids, and you still have the drag errors to be less than 0.1% or something. The numerics is expensive, but the data that it generates has a lot more regularity. So you end up, you can exploit that regularity to downsample, and in time, you don't even need any time stepping, because you're just interested in the long, sort of large time step or the large horizon, long horizon, steady state computations. So you don't have to go through all these intermediate scales in space and time. You can directly learn the input-output relationships, and these are very, very regular. And this is the reason why neural networks work very well, because they directly work with data, and they don't have to go through the intricate process of generating data. Is that clear?
Got it. Thank you. Yeah, thank you.
Okay. So this is the reason. If there was no regularity, if we are just looking at noise, then the neural network will not be, and you'll see in the next problem that this comes into the fore in a very critical way. So this is great, right? We can do all these industrially realistic problems, and there is big money these days in doing it. But physics is rather forbidding, right? It's sort of, you'll see, this is an example. This is just fluid dynamics in 3D. And there is no complex geometry here. It's on a box, right? So things are simple. But now what you're seeing is a particular initial condition called Taylor-Green initial conditions. Anyone who has studied basic physics in university or basic fluid dynamics in university knows this. And what you see here is the solutions which generated with the numerical method, the spectral viscosity method, but that's the detail. So what you see in this panel here are so let's focus on this. You see that a lot of small scales are being generated. This is like a real flow. If you go outside and you'll visualize wind or water, there are lots of small scales that are being generated, right? And the second thing is that these are the outputs of the kinetic energy. So we visualize using the kinetic energy for very, very close initial conditions. The initial conditions are tiny perturbations. If I showed them, you would not be able to discern the difference. But now when you look at the solution, it's a chaotic system. Means things, there is very extreme sensitivity to initial conditions or conditions. So if you focus on this quadrant, you have very, very different behavior, right? So this is what you want to capture. Now, when you give this input to neural networks and neural operators, means it's just semantics here, and it doesn't matter which model you give it to, means what you end up is this, that it's sort of, you don't get this variance at all, and you don't get the small scales at all. So you somehow regress just to the mean. So now you could say maybe your model is very bad, right? Neural networks are, neural operators are universal function approximators or universal operator approximators. In principle, they should be able to represent these objects. So why are they not able to do that? There's nothing to do with the expressivity of neural networks, but it has to do with training, right? So, and the loss functions and so on. So what happens, and this is very intuitive, is the neural networks, particularly when we train them with gradient descent, the gradients have to be somehow bounded. These have to be of order of 1. They can't be too small or too large, right? We know that. Now, once this happens, this is not good for us, because what happens is that if I make a tiny change here, then expand in Taylor series, my Lipschitz constant is small, so I can, and this perturbation is small, so the second order term goes, and I'm just ending up with not seeing this sensitivity, right? But the ground truth exactly has the sensitivity. Tiny perturbations grow, right? Whereas for the neural network, tiny perturbations are not even seen in some sense. Of course, it's an assumption, right? So once I make this kind of an assumption that essentially neural networks are well-behaved gradients, then the whole picture becomes very clear, because this is the ground truth, right? So the ground truth, you make tiny perturbations, nothing changes, means you can't collapse. Neural network, it collapses. And then you just do a standard Bayes variance decomposition. And what happens is that you get a term, the variance, which is nothing to do with neural networks. It has to do with your system itself. And you see that the variance here is order of 1, right? It's not a small term. So this doesn't vanish. You can't really train because it's a perfect sum of squares. And this one here, the best you can do, where theta is the trainable parameters are there, it just collapses to the mean. And this happens time and again. So unless until, so if the problem is such that there is sensitive dependence to initial conditions, if you use neural networks, try to minimize the least squares error or absolute error, you'll end up with this. And this is exactly what you observe time and again. So what's the solution then, right? Because it seems like an insurmountable problem. So the understanding is that in this case, going and trying to learn every single whirl, every single eddy, every single vortex is pointless, cannot be done. Rather, one has to look for some statistical regularity, some statistical behavior. And in my avatar as a fluid dynamicist, a mathematical fluid dynamicist, this is what I have studied extensively, that the statistical behavior of the systems is well-behaved. These are well-behaved statistically, even though deterministically, this is the whole essence of chaos, that you have some stability statistically. So what we could learn is actually conditional distributions, because given some initial condition, we can learn the distribution that we are going to get out of it, rather than each deterministic trajectory, right? So this is the basic idea. And of course, to this audience, I don't have to say how we learn conditional distributions. Means, there are many ways in ML these days to learn it, but I'm going to, and we have used different ways, flow matching and so on and so forth. But for this talk, let me focus on score-based diffusion models, right? So we have a noising process where we add noise, and then we solve the reverse STE in order to denoise and to capture the conditional distribution from the input. So this is the basic idea. Now, what we did is that we applied this with some small modifications, which are technical details, to fluid dynamics, particularly to this chaotic fluid dynamics. And this led to what is called the Gen CFT algorithm. This was actually done with colleagues at Google Research. And the idea is the following, that during training, this is standard, you take your initial condition, for instance, as your prompt, as your conditional input, you take your solution and add noise to it and try to denoise it, right? So now the same neural network, but I'm giving it a different task. And the task is, given a noisy output, I denoise it. This is not having this exponential separation that was in forward in time prediction. So by changing the perspective, I make the task of the neural network much more easy and much more doable in some sense. And once this is done, then you put the denoiser into the, as a score function, into the SDE, and then use the evolution of the SDE in order to predict the behavior or the trajectory of fluid motion. And then, at least for some simple systems, we can even prove end-to-end that this approximates the correct conditional distribution. So now let's look at the results here, right? So remember that this is what I saw in the beginning, that I took my ground truth and I took the neural network, trained it to regress, and this completely collapsed, right? Now it is almost impossible to distinguish between the ground truth and what my algorithm provides. It was able to generate the correct distribution. And you see it in the velocity, you see it in the vorticity, you see it in the variance. So earlier there was a collapse in the variance. It collapsed, everything collapsed to the mean. But now the right kind of variance is captured. Also the small scales are captured. So the right sort of scale decay, which is essential for fluid flows. And needless to say, all the statistical metrics, there was orders and orders of magnitude improvement. So thanks to this twist, we were essentially able to solve this problem. And once you can do it on a challenging academic problem, you can scale it up. So for instance, this is a flow from a chimney, smoke coming out of a chimney or a nozzle. And if you just use plain vanilla ML, you just get the central jet. You don't get the smoke, the sort of eddies and the whirls of the smoke. And this is what Gen CFT is able to do with realistic accuracy. It means it's quite accurate. You know, there's only 5% error on the variance, which is the hardest thing to capture here. And you can do it for atmospheric flows, you can do it for shock waves and so on. And at the end of the day, what you save is certainly computational time, right? This was 15 hours or 14 hours of simulation. Now this is just 3 to 4 seconds. So it's really, and we can reduce it even further with rectified flows and so on. But the essential point is that we're able to map this mathematical problem into something in standard machine learning, generative modeling, and we are able to solve it. So this was so I think it's a success story in that sense. But I will hurry up a little bit. Yes, go ahead.
What are the data requirements of this? Like how little data can you get away with in creating this?
Yes, you hit the nail on the head.
Okay.
You hit the nail on the head. Because of course, this is the natural question that comes in, right? So these models, just like any statistical machine learning model, they scale, means we see scaling laws. We can even prove some scaling laws because there is some natural regularity in these problems. So we can mathematically know what the regularity is, and we can even prove some scaling laws. But scaling here is the exponent here. Of course, it can't be better in general than 0.5, but in practice, it is something like 0.4, means 0.3, 0.4, which means that you need loads of data to get engineering accuracy. So to get 1% accuracy, you see the 1 is here, where barely this model here is touching CNO, convolutional operator is barely touching it in this particular problem. And you can see 2 to the power 13 is like 10,000 samples, right? So you need a lot of, also this model here, to do this, you require something of the order of 5 to 10,000 samples. So these are very, very data hungry. And now we don't have internet scale data sets, because remember that to generate each flow around a car was 60,000, right? So node hours, so we don't have 10,000. So essentially, that's the main challenge, that you have to make these things work in a data scarce regime, because there's no abundant data out there, except in weather modeling. There you have a lot of data. And in particle physics, of course. But in general, for engineering, for general physics, you don't have the data. It's very, very expensive. So what do we do? Means this is a good question, and I will more or less finish very quickly with this, is we have to build foundation models. Right? Foundation models is how the community has answered that you can specialize based on some generalistic models, and we want to take that into physics, into general purpose physics. And just for mental mapping, I use PDEs here because then it's easy to state things. So you can imagine that there are different kinds of PDEs describing different kinds of physics. So this could be the wave equation, wave propagation, Navier-Stokes, elasticity, Poisson's equation describing diffusion, and so on. And for each of these, you can change the domain, the boundary conditions, the initial conditions, the coefficients, the operating conditions. You end up with an infinitude of operators, right? So you have infinite number of PDEs, infinitude of operators. And if you want to take the foundation model paradigm seriously, you can only train on a few of them, learn some general physics, and then you should be able to fine-tune a test or at task-specific time, adapt them for a different PDE. Right? So this is sort of the basic thing. But anyone who has taken freshman physics, mathematical physics, and takes a textbook, this seems to be weird, right? Because PDEs like Laplace's equation, wave equation, Navier-Stokes, these seem to be totally disconnected from each other. These are different chapters in a textbook, right? So how can you leverage this? They seem to be like silos which are not communicating with each other. So I also felt that that's the case. But let's try it out. Let's build something and see whether we can leverage some hidden connections, right? And the attempt of it is Poseidon. This was released a little less than 2 years ago. And the idea is that we do exactly what I just said, that it is trained on, it's a proof of concept. It's not a world model in that sense. It's a proof of concept. And the idea is that you train on some operators coming from a very small finite set of PDEs. We chose 2D Cartesian grids as a proof of principle. And it is trained only on two equations, both from fluid dynamics, one the equations of incompressible fluid dynamics and the other of compressible fluid dynamics, so that you have shock waves and so on. And this pre-training data goes into a Swin transformer, and which I've described before. There is some special tricks for how you take time integration into account. But at the end of the day, we have approximately 5 million image pairs. And our largest model that we released is 630 million parameters. We have bigger models now, but that was the public release at least, right? So now it is pre-trained on fluid dynamics. The question is, does it transfer to unknown physics, right? And to do that, of course, we have to fine-tune. I don't have to describe the details here. You can either transfer the entire model, you can start from the entire model, or you can transfer just the latent space. And what we want to measure is how much of data requirement can be reduced, right? So essentially, if I have a baseline model, which is just task specific, and I give it 1,000 task specific samples, can I get down to 50 or 40 so that the data requirements are gone down? Or for a fixed number of samples, let's say 100, how much do I reduce in terms of the error? So these are the two metrics that we looked at. And the final answer is, and this was tested on 15 different tasks, some of them on fluid dynamics, some of them on not at all on fluid dynamics. For instance, this is wave propagation here, reaction diffusion, pure diffusion, Helmholtz, so this is electromagnetic or acoustic wave propagation and so on. Physics that is different from what is learned, and physics that is in distribution in some sense, right? And what we observed is that the foundation model worked very well, actually. On a median basis, it was like 50 times more data efficient. So earlier, if I needed 10,000 samples, if this holds, I need 200 samples, right? So you can scale it up. And if I have a fixed number of samples, it was 10 times more accurate. It scaled with the model size, you know, as we increased it, it scaled with model size and so on. So this was very good news if we wanted to do scarce or data efficient machine learning. But the question is, this is a proof of concept, it's in 2D, academic. Can we scale it to 3D? Can we scale it to this very complex engineering type problems? Can we bring in chaotic fluid dynamics and so on? And yeah, before that, just to show you that it works, here is a classic example. So it has been trained on fluid dynamics. This is just diffusion. You put in some Gaussian forces and you let the effect diffuse out. So that's the basic idea. It has not learned diffusion. It has not seen diffusion. But very quickly, with 16 samples, it is able to qualitatively learn diffusion because it has some rich physical information that it is able to leverage. Even when the latent space is frozen, it is able to leverage that. And as you give it more samples, more data, it's able to learn something that it would have otherwise required 1,000 samples, right? So this is sort of the, let's say, the trick or the foundation on which we think that you can do some data efficient learning. But the challenge is, of course, can we scale it to the real world? And this is what is ongoing research. I can only tell you that we are training such a model. We don't have the final answer yet, but we want to have different kinds of physics: wave propagation, cloud dynamics, fluid mechanics, both interior fluid mechanics and exterior fluid mechanics, fluid structure interaction, computational electromagnetics, computational solid mechanics, a lot of sort of human scale physics, put it into a single model and see whether we can train it together and whether we can sort of transfer it to tasks. And we have a prototype which is running in 3D with all the complexities that I've described before. So it has been trained on fluid dynamics, including some of the data sets that I just showed you, wave propagation, diffusion, external fluid dynamics on cars and planes or wings. And it trains well, and it shows some skill at fine tuning, but this still needs to be done, right? So this is sort of the main challenge in some sense. So let me quickly come to my summary slide. Yes, is there a question?
Yes, the last point that you mentioned is intriguing, the more structural symbolic information, because to me, is, if I am thinking of myself, the student doing this, learning this stuff, I'm thinking, this is fluids, this is nuclear, this is ecologies. And that tells me exactly what family of dynamics I'm going to be watching out for in a way that data points are sparse. So have you tried using fine-tuning a llama, a gemma, or whatnot alongside one of these things to give you those embeddings?
This is a very, very good question. I haven't done it. I know some other people have done it. I will give you two answers, right? So first of all, I know some people have taken llama and they have tried to use that as a prior. I think the success there has been pretty middling. They are nowhere close to the kind of accuracy that we want in some sense. What we have done is that we have taken some video diffusion models, much smaller than llama or gemma, and we have tried to, for instance, model urban wind flow using those video diffusion models to some success. These were more useful. World models are more useful priors. The problem is, of course, that of accuracy. The flow looks plausible, but plausibility ain't close enough, right? It's not. You need something more. You need this to be within 1-2% of the ground truth, and this is what is the problem. It gives you plausible-looking fields, but not. It's not the real thing. So I think it could be useful, but it's also an engineering challenge. Now, a very big model. You're working in the space of tokens, right? And we have also done some tokenization work, which is, at the moment, the science is not there. But once we learn how to tokenize these very complex fields into a common token space, I think there are some good science even from my own lab, then perhaps there is a chance. But at the moment, let me tell you that this is these priors, we have not been able to leverage them properly, right? So symbolic information was more to be given as a direct multimodal input, right? And even there, I'm sort of skeptical because otherwise you would have never done what we have done here. Because the symbol for fluid dynamics, the PDEs look very, very different from this guy here. So so by sort of not putting those explicit biases, I think the model somehow learned some physical relationships which were very useful to it later on. So I think the jury is out. Maybe we don't know how to do it yet, but certainly this is a viable option. Does that answer your question?
Thank you.
Yes. So let me now come to my summary slide. So as I said, you want to use neural networks or AI models for physics, and in some sense, we are able to do that at some scale, right? So you can do it on very complex domains for complex engineering problems. You can even do it for multiscale chaotic PDEs. And what I didn't show you, partly because some of it is confidential, is that we can directly learn from experimental data. We don't need to go through synthetic data at all. But the main challenge, as one of you identified so appropriately, is sample efficiency, because this requires a lot of data that we don't necessarily have. So my own perspective is that the only way we can sort of work this out is by building foundation or world models, physical world models in that sense. There are some very good green shoots out there, some good proofs of concepts, but to really scale it industrially is a big, big challenge. But once this is done, then it opens up a lot of doors. Inverse design, uncertainty quantification, all of this become much more doable, because the cost of iterating is going to be super fast. And there's, of course, there's a question of trust and so on. Means you need these models to be fairly accurate and you need to trust them. But there's some other work that we have done, but today is not the time to describe it. So thank you very much for your attention and also for the questions. And if there's time, I'm happy to take some further questions. So thank you very much.
Yeah, absolutely. Thank you. So yeah, here's one question. So this work straddles the boundary between discovering the driving PDEs and finding a solution, an efficient solution to driving PDEs. So I'm going to focus on like ecology, climate, where the full PDEs are not quite known, too expensive to simulate, and ecology, they're plain not known. So to what extent are these technologies useful for that? The less structured domain, like the available knowledge is, let's say, maybe scattered. There's a lot of ideas, but we don't know which ones are right.
This is a very, very good question. So actually, here is the little sort of secret, right? The big reveal, that all the things that I did, the fact that there was a PDE or set of PDEs underlying the data was almost never used by us, So this was totally sort of agnostic to the PDEs that were there. What we did use is to prove some theorems on paper. We have used the structure and we have used the regularity. But in the actual architecture itself, on purpose, because we want to apply to domains like ecology and so on, where no one knows what is going on, right? And yet we have some data, potentially sparse, potentially related with the physics that we are going to see. So that's why we are sort of very interested in this space, because ultimate aim is to get rid of these sim to real gaps, to understand systems that have hitherto not been understood, right? Primarily because you cannot sit and write down first principles physics. What are the conservation laws, conservation of energy, momentum, blah. But this is not possible in certain contexts. What you have data, and from that data, you have to learn some regularity structures, which we don't know yet. Perhaps the model learns it. It can help us learn this. And that, to me, is sort of the most interesting element, that we don't really need any information. These models are completely agnostic to the actual PDE itself. These are some transformers, some graphs, which have been used in image and vision and text and so on, right?
So let me push that along. One benefit of having structured PDEs is explainability, which is a poorly defined term, but I'm going to focus it on multiscale. I have a clear idea of how different scales couple because I have common terminology across all the scales because they are quote unquote interpretable. Now, what is your thinking about the ability of these technologies to connect across domains? Are you simply going to demand data across all domains and train one giant operator? Or is there a notion of explainability, structure, or embedding interfaces that allow you to do multiscale?
This is an excellent question. And to be honest, I don't have a definitive answer, but I can give you a thesis, right? It's not an answer, but it's rather a thesis. And the following, that at the moment, the data that you feed into these big models, this is essentially resting in my head or their designer's head, right? It's based on intuition. And this intuition comes from working on PDEs for a long time. It's not some random sample. Why did I choose the Euler equations, the Navier-Stokes equations? Because I know that these are more complex PDEs, where there are a lot of complex features that are being learned. And essentially, in our head, we have a mental model of the important physical domains: thermal, electromagnetics, structural mechanics, fluid structure interaction, multiscale fluids, and so on. But there is no sort of theory or, let's say, paradigm for explainability that I have at the moment to do that. So the idea, I think, not just me, but the community, is we build these models, just like people in text and vision did. We build these models, we see how well they work, and once we have established that they work, we try to sort of peel into the inner layers and try to see whether the traditional sort of mechanistic interpretability and these other ideas can scale here. I believe that this is possible because we have a lot more physical priors about physics than we do about text and vision, right? Means it's sort of, so I think this is a more sort of fruitful avenue for being able to do something here. But at the moment, there is no answer to that question because it's very challenging, right? Because why I have theories, of course, that's why I put them in the first place.
Right.
But these theories have very little sort of solid evidence behind them.
Got it. Well, thank you very much. It was fascinating.
Yeah, it was my pleasure, and thank you.